Um, so what I want to talk about is spherical integration, and more specifically, how to represent dv in spherical coordinates. Now we already know that dv is dz, dy, dx, or any different combinations of it in rectangular coordinates. You don't have to be in this order. It could be dx, dy, dz, or any other order. And what about if you write in terms of polar, or actually cylindrical coordinate system? R dr d theta, right? And then because dz doesn't change when you go from the rectangular to cylindrical, dz stays the same, but r dr d theta will be replacing dx dy. So dy dx will be replaced by r dr d theta. That's what happens. Okay? And again, this order doesn't have to be always in this order, but usually that's how you want it. These are the most typical orders that people use. Now what I'm trying to get at is actually, what do you need when you want d rho, d theta, d phi? Now let me explain that further. See, I took some time to explain why we need that r when you go from rectangular to polar. Right? And the reason for that was if you calculate the Jacobian of this transformation, you get this r. That's how I explained it, right? And therefore, when you try to go from here to there, you would also get some kind of a Jacobian. And the question is, what do we need? That's the question. Right? So actually, let's do the computation. First, we know that a priori that the thing that fits here to go from here to there would be derivative of something over derivative of something, and we have to take the determinant. Let's see. These things should cancel with this, so I should have rho theta phi here. And then also when these two are canceled, I need it to produce that, so it must be x, y, z. Or you can do z, y, x, doesn't matter, but let's stick to x, y, z. Okay. So dx, dy, dz is something times d rho, d theta, d phi. That's what I want. And in order to calculate this, what is this thing again? You're trying to differentiate x by rho, x by theta, x by phi, y by rho, y by theta, y by phi, z by rho, and you have to think about all possible combinations of the derivatives, all possible combinations of partial derivatives, which gives you a gigantic matrix, and you take the determinant. That's what places here, right? Now, that means I have to know what x is in terms of rho theta phi, what y is in terms of rho theta phi, and z is in terms of rho theta phi. So let's think about that. So here's what I know. I know that in order to go from x, y to cylindrical, I have x equal to r cosine theta, and y equal to r sine theta, and z is equal to z. This is the formula that gives you the relationship between the cylindrical coordinate system and the rectangular coordinate system, right? Z doesn't change, but x and y are related to r and theta in this way. Now, to give you a relationship between these two, I actually don't know the formula, so I have to derive it in front of you. And I don't really feel a need to memorize the formula because I just have a single nice picture that where I can use to find the formula easily, right? So the formula is if phi is the angle from the North Pole, then rho is the distance from the origin to that point given, so rho is this distance. R is the distance from the point to the z-axis, this is the z-axis, and z is the height of this given point that I want to describe. Okay? And this right triangle is the only thing that you have to remember in order to remember the relationship between this and that. Okay? Now from here we can easily find the relationship between r, rho, and z and phi. Okay, how do you get the z from rho and phi? Rho times cosine phi. right? Because phi is the angle between z and rho, so z is adjacent. Soka to us says, oh, if you want the adjacent, you multiply the cosine. Right? How about r? R is the opposite, right? So what do you do? Rho times sine phi. So that's the relationship between the cylindrical and the spherical, because when you go from cylindrical to spherical, theta doesn't change. You only need to know how to get the z and r. Right? Now, if I put these two together, then it gives me the relationship between x, y, z and rho phi, because see, x is r cosine theta and r is rho sine phi. So if I take this and replace this r, I get the relation that x must be rho sine phi times cosine theta. Y must be rho sine phi times sine theta. And z must be, well, z is here. Z is rho cosine phi. So that gives me the relationship between rho phi theta and x, y, and z. That's the relationship. Now, what do we need to do again? Why are we doing this? I want to differentiate, right? So I have to differentiate x, y, and z with respect to rho theta phi and come up with this gigantic matrix and compute that matrix. Compute the determinant of that matrix. Okay? All right, so first, if I take this and differentiate by rho, what do I get? Sine phi cosine theta, right? If I differentiate by rho, these are partial derivatives, which means you take the other variables as constants. So if you're differentiating by rho, you're differentiating rho by rho, and these are constants. So this is what we get. Okay? And then what do I differentiate next? By theta, right? So if I differentiate this by theta, these are considered as constants, so you're only differentiating cosine theta, which gives us negative sine theta, right? So it's negative rho sine phi sine theta. Okay, now you differentiate x by phi. X by phi. X by rho, x by theta, x by phi. Okay. If I differentiate x by phi, you get cosine phi, yes, cosine phi, and then cosine theta. All right, next I have to do y by rho. If I differentiate this by rho differentiated by rho is just 1, so I get sine phi, sine theta. Okay, and then if I differentiate y by theta, I get rho sine phi cosine theta, because I'm differentiating sine theta by theta, right? And then I differentiate this by phi, which gives you cosine phi. So it's rho cosine phi, and then sine theta. No. If you differentiate sine phi by phi, it's positive cosine. Okay, now we have to differentiate z by rho. So if I differentiate this by rho, I get cosine phi. If I differentiate this by theta, what do I get? If I differentiate this by theta. So you have to differentiate z by rho, z by theta, z by phi. So if I differentiate this by theta, what do I get?
Rho cosine.
These are considered as what?
Constants.
If you differentiate this constant by theta, you get?
By theta.
No, that's how you integrate a constant. If you differentiate a constant, you get?
0.
0. If you differentiate a constant, you get 0. Okay, and then if you differentiate by phi, that's negative rho sine phi. Okay, so this humongous matrix is what we have to use for this. Okay, so I computed this and got this, and now finally I have to take the determinant. All right, and then we have to take the determinant, right? How do I take the determinant? I have to do something like row expansion or column expansion, right? So if I do column expansion this way, this times the determinant of that, which is like that. So sine phi times cosine phi, and also you get sine squared. And if you multiply these, you again get sine phi times cosine phi, but cosine squared. And minus minus gives you, you end up adding the sine squared and cosine squared. It'll be a 1. And at the end of the day, you're going to get cosine phi multiplied by sine phi cosine phi. All right, so it's a long calculation, and I don't think I want to bore you to death with this. If you have time, try to calculate this. You're going to get the following answer. You're going to get rho squared sine phi. That's what it's going to end up being. Okay. All right. So that's what it is. So you get this important result, which is that if you write down dv, you get rho squared sine phi times d rho d theta d phi. That's what you get. You get rho squared sine phi d rho d theta d phi. Now I may have forgotten about this. It's actually determinant with the absolute value, so if you compute this, you might end up with a minus at the end of the day. You just have to change that to plus, okay? Because this is really determinant with an absolute value. Right? Okay, so you get this. And if you understood everything that I did so far, that's great. If you didn't, it's okay. All I require to know is this. The fact that you need the rho squared sine phi in order to do integration in the spherical coordinates. Okay? Just like you needed r for integration in cylindrical, you need rho squared sine phi to do spherical integration. So r for cylindrical or polar, rho squared sine phi for spherical. That's what you need to know. Now, since that calculation wasn't so elaborating, let me try to provide you with two other approaches to see why this makes sense. Okay? Now, first approach is a very crude one. You use the units, just like how we use the units to verify that you need something like r in front when we go to polar. We can do the same thing. Okay? So dV, in MKS units, what's the unit for the volume? Meters cubed, right? That's the volume unit for the volume. Right, d rho, that's the small increment for the length, right? So what's the unit for d rho? Meters, right? How about angles? What's the unit for angles? It's radians, but in MKS units, I told you that it's unitless, right? So these don't have any units. D rho has a unit of meters, and this is meters cubed. So think about it. If you didn't have this, you're basically trying to equate something that's cubic meters to something that has meters. That doesn't make any sense at all, right? So now, let's see what happens if you included this. Rho is meters, so rho squared is square meters. Sine, trigonometric functions are ratios of two lengths, so that's unitless, okay? That doesn't have any unit. So you have meters squared times meters, which gives you cubic meters, which does match with the unit on the left, okay? So that's a crude argument, but it really helps you to memorize this, because if you just notice that I need cubic meters, so I need meters, 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 but this only provides 1 meter, then I definitely need something squared so that I can have a square meters. Okay? That's how you remember that you need rho squared. If you did have that argument, then it would be hard to remember whether this was a cube or a first power or a second power. It's hard to remember which is which. But now with this argument, you know that it should be rho squared. That's the only thing that will match the units left and right. Okay? So that's the first crude argument. Now, a slightly more geometric argument goes like this. So first, think about this as rho times rho sine phi And what is rho sine phi? I raised it, but it's really r equals to rho sine phi, right? This is really equal to r. So you can think of this as rho times r, d rho, d theta, d phi. And furthermore, you can rewrite this as d rho times d rho times r d theta and rho d phi. Okay. And let's try to make sense out of this. So if you think about d phi, what is d phi? D phi is a small increment in the angle from the North Pole, right? So if you have the North Pole and you come down for about phi, and then from here you come down slightly more so that you get a very small increment in that direction. It's supposed to be smaller, but I couldn't draw smaller, so this is d phi. So this small increment in the phi direction is d phi. And then what is d theta? D theta is like rotating like this in the with respect to z as your axis. That's d theta. Right? So d theta is more like how do I say it? It's more like this. Okay, where if you projected this down, the angle that you have is this is your d theta. So it's like this. That's your d theta. Right? Now, if you have d phi and you multiply by this length rho, what do you get? You get this length, right? Is that right? That's just from SOR. SOR formula says the arc length is same as the central angle times the radius. If you think about this arc, the central angle is d phi and the radius is rho. So if you multiply rho times d phi, you get this length, which is rho d phi. And then for the same reason, if this is r, and you have this angle d theta, this length is dr, which is same as this one here. Okay? So that's your r d theta. And then finally, what is d rho? D rho is the increment in the rho direction. So you can think about this very small tiny box whose increment is d rho. And then if these angles are very, very small, you can think of this box as actually a box whose width is rho d phi, length is r d theta, whose height is d rho. So what's the volume? Volume is this times that, right? So that's why that's equal to dV. Right? So that's a purely geometrical argument, which may not be so convincing. It might be too complicated. So you choose which one makes more sense to you. I kind of like this one better because it's straightforward and you calculate everything. But if that's too much, then you can try to see that this works. Okay. But at the end of the day, what you need to know is that you need the rho squared sine phi.